Chapter 24, Carbonyl Condensation Reactions. In a sense, Chapter 24 is a continuation of Chapter 23, where we discussed enolates, enols as nucleophiles reacting with electrophiles. But in Chapter 24, it's a little bit different. We have, in this case, as we discussed, we have enols and enolates. We know that they are electron-rich nucleophiles, as you can see here, that can react with a number of different electrophiles. But now what we're going to discuss in this chapter is that they're going to actually react with other carbonyls. So let's see what that means. So let's just get the colors here ready. So we know that this is delta plus, and this is delta minus. We know that if we have a base, it's going to deprotonate one of those H's, a lone pair. Again, we have an electron-rich nucleophile. So in this case, you have an enolate. And you notice that the enolate as a nucleophile attacks the electrophile. Here it is added right there. So in the last chapter, we talked about Br2 as an electrophile where we added a halogen. We talked about Rx, like an alkyl halide where we added an alkyl group, something like, for example, CH3Br, CH3I, etc. We did the alkylation. But again, as we said in this chapter, we're going to have enolates reacting with carbonyl compounds. So the question is, what if the electrophile was another carbonyl compound? The answer is you have what we call a condensation reaction. So you will have a condensation reaction. So remember, when you have an enolate reacting with a carbonyl, in a sense, they are both carbonyls, you will have a condensation. You're adding them together. Okay, so what is the name of the reaction that involves an enol or an enolate? We're going to focus mostly on enolates with an aldehyde or a ketone. There's a name for this. We call it an aldol addition or aldol condensation. So the aldol condensation is a slightly different one. In this case, the enol and the enolate are your nucleophiles. And of course, your aldehyde or the ketone are the electrophile. So let's put a negative. Well, it could change. So we can put a lone pair here. As far as if you have an enolate and an ester, the enolate will be your nucleophile, and the ester will be your electrophile. And there's a name for this. We call this the Claisen condensation. So make sure you know the distinction. This is an important distinction. We're going to focus only on 3 reactions, but they are big reactions. Claisen, aldol, and the Michael addition. So this is the focus of this chapter. Now, let's focus on the aldol addition, aldol condensation. So we're going to focus only on base catalyzed, just like your book. So what you need to pay attention to this 2, okay? This 2 means you have 2 of these, 2 moles. Plus another one. Now, for this chapter, just the heads up here, make sure you really keep track of your carbons, because you will have, it's no longer like, just adding an R group or bromine somewhere. Here, when you add to a carbonyl, you already have a large structure to begin with. Now you're adding another structure. So you're going to have a bigger product than both. So this is what you have. You have 2 aldehydes, 2 moles of an aldehyde, acetaldehyde. And what's going to happen is that when you have base catalyzed, sodium hydroxide is your base, you will have this outcome. Okay, so this is called an aldol addition. So this is the addition, and I'm going to help you see how this happens. We're going to talk about the mechanism, but let's mark some things here. So supposedly you have to remember which one is your alpha in this case. So supposedly this was the alpha. Okay, it became, we're going to show you the mechanism, like I said, on the next page. So this would be the alpha right here. Okay. Now, the next carbon, remember, is the beta. Okay. So this is alpha, and I'm going to put beta on this so you can see. Nope, 1 second, not that one. So you can see the connections that was made. So basically there was an attack. There was a lone pair, attack this, form this. Like I said, I will show you in a second, but let me actually highlight it. That would be actually better. Let me delete the beta because it's the carbonyl, but I just was trying to show you. So this is the yellow. Here it is. I'm choosing that one. And then this is the green. Here it is. We know the attack at the carbonyl results in breaking the double bond, the carbonyl double bond. All right, so there's a name for this. We call this a beta hydroxy carbonyl. And it makes sense. You have a hydroxy, and it's on the beta position. And of course, you have a carbonyl. Now, if this reaction undergoes dehydration, so you have a base, and that's a dehydration, getting rid of water, then it will turn into the condensation product. Okay, so basically, I don't want to mark too much here, not to confuse you, but imagine this OH, and then one of these H's, one of those H's, if you lose the OH and an H here, then there has to be a double bond formed in between. So I'm going to show you here what's left over. You have an H, that's this H, and then there's another H. So one of the H's was lost. Actually, let me redraw this so you can see it better. So this was the yellow we said. This was the green. So here's water being lost. That's why it's called dehydration. OH and then H, that's H2O. Of course, then there has to be a double bond formed in between to form the octet. So that's aldol condensation. So the question is, what's going on here? As I said before, you have an enolate attacking a carbonyl. So here it is. Let's draw it out, what we had before. So here's your enolate. Put the negative there. Once again, you can have the double bond instead. That works. But let's just show it this way. All right, so you formed on one of these, one of the H's was deprotonated, forming an enolate. So we know that this is an electron-rich nucleophile. And we need to draw the electrophile, the electrophilic carbon. The carbonyl is an electrophilic carbon. Let's put the electrons on here. And of course, this is delta minus in on oxygen. It's more electronegative. So what's happening here is you have an electron pour electrophile. Which is the carbon and the carbon. Notice that the carbon here is your nucleophile, and notice that this carbon now is your electrophile. So electrophile, nucleophile is attracted, attacks, and forms the following. Okay, so we need to really mark them. So I'm going to put yellow, and this is green, so you can see it. So you can see the connection. If it helps you, go ahead and use it. But let's start. Here's the H. Carbonyl, carbon, oxygen, and now here's our CH2. Okay, so the bond was formed between alpha carbon here and the carbonyl on the other one. So let's mark this here. Look, the most important thing is knowing how to form that bond between the carbonyl in the electrophile and the alpha carbon in the nucleophile. So of course, this double bond was broken. Oxygen became negatively charged. We have a CH3. And of course, we have an H. So really make sure you absorb this and understand it. So then what happens is we have protonation, as you would have expected. And you should know why we have a protonation. It should be very clear why we have a protonation, not kicking out a group, because none of these is actually a good leaving group. Okay, so these are bad leaving groups. Okay, almost impossible for them to leave. So after you protonate this, you form the beta hydroxycarbonyl. Okay, now I'm going to draw out, like I said, those H's. Let me put one on the top and one on the bottom so you can easily see what's happening here. Okay, so now we're going to do dehydration. Notice that what I am highlighting is essentially water, right? So I'm going to show you that if this leaves, just to show you the arrows, in a sense, the mechanism, we're going to show you the mechanism in a sense, but there's a double bond forming here. This is breaking. And as I said, we have heat and AOH. So we have dehydration, loss of water, minus water means we're getting rid of water. And then we have our aldol condensation product. Okay, so let's talk about the mechanism. I mean, essentially, the mechanism, you can probably read it from the scheme that I just showed you. But of course, there are stepwise mechanism, and we have to discuss it. So be patient with this video. So let's look at the mechanism. So first, we're going to take one of the aldehyde molecules, and remember, we're going to form an enolate. So if we go back here to the scheme, we started with sodium hydroxide. It's a base. It will deprotonate the alpha carbon. So in this case, the negative on this. We formed now our enolate. So we have to form our enolate. Remember, this is nothing new. This was discussed in chapter 23. Now you have the other mole of the aldehyde. Remember, delta plus, delta minus, plus, delta minus. Here it is. Let's bring this down here for more space. So we have okay. So now we have to protonate. So we have water. That's basically this step right here. So we're going to remember what I said. I'm going to put the H's one up and one down. You don't have to do that, but I have to so I can show you. So we have now the OH, the CH3, and the H. Okay, so now the dehydration step is now you have the base. So the base is going to attack the strongly acidic proton on the alpha, remember? Okay, so that's really the mechanism is what happens is you deprotonate the alpha proton, electrons shift, form a double bond, and then of course the carbonyl double bond breaks. So that forms and we need to actually get rid of those arrows for now. I just need more space here. Very well. And now, lastly, what's going to happen is that these electrons on the oxygen are going to shift down double bond electrons are going to move one bond over and kick the OH out. And finally, this yields our condensation product. Let's fix up this bond. As you can see, this is the same as that. We can hear. Or actually, let me put this back here. So that's it. So it's important to remember the steps. First step is you do the attack, you make the enolate, and then essentially when you get to the dehydration, you have to get rid of the OH and you form the condensation product.